The presentation of today is going to be about evacuation modeling in COVID-19. So I will talk about the implications that the current pandemic has on the way we calibrate inputs for evacuation models, and also I will present a sub-model that I've been developing along with some colleagues for retrofitting crowd evacuation models and perform risk assessment linked to coronavirus transmission. First of all, I would like to acknowledge some of my collaborators, in particular the sponsor, Cantene from Italy, that has been sponsoring this work, in particular Rugiada Scozzari and Michele Fronterre, and also some colleagues that have worked with me on different aspects of COVID-19 and the implication on evacuation modeling, Ruggero Aurelio, Håkan Francis, and Daniel Nilsson. So, the outline of this presentation is first a very general introduction about the issues linked to COVID-19, something that has been affecting all stakeholders involved in crowd modeling. And then there's been a lot of talking about physical distancing around the world, and we will see what are the main implications that this has on evacuation simulations. After this, there will be a part in which I will talk about two different ways of dealing with the consequences of COVID-19 when it comes to performing a risk analysis, and those consist in proximity analysis, which is quite common nowadays, is getting more and more common, but also exposure assessment during evacuation. So I will explain a bit the difference between these two, and why, at least my point of view, is that exposure assessment is a bit more complete than proximity analysis. After this, I will present this new model called Exposed. This is a model which is basically a sub-model made to retrofit any evacuation model as long as it is able to produce outputs concerning the coordinates of the agents in space, which is a very common output that this can be produced by microscopic agent-based models. And I will explain a bit how it works, what is the concept behind, and potential future uses of it. And finally, I will conclude with a discussion on the methodology on how we should use, or we could use at least, evacuation models during COVID-19. So basically, how do we deal with the case of concurrent threats? So we are in a situation in which we want to both do a fire safety engineering analysis, but also we have to deal with the threat coming from the pandemic. Basically, the main motivation for this work is that we are dealing with a situation in which we may have concurrent threats, because we know that the pandemic can have a quite important effect on crowd dynamics. Indeed, the field of crowd dynamics has been in the spotlight in this period as probably as never before, which means that more and more people are interested in understanding how people move, due to the fact that indeed the movement has implications on the risk of virus transmission. The problem that we have is that we still have quite scarce empirical research available concerning crowd dynamics in times of pandemic. So I'm aware of a couple of research groups that are starting doing some data collection. I've started doing some data collection, or I've initially done that, but there is not so much data already available that we can use and directly implement in models. And mostly what I've seen so far is mostly for normal situations. So there will be the need to do some sort of extrapolation from those data for evacuation modeling applications, or for emergency scenarios. And the problem is that it's not that since we are in a situation in which we have COVID-19, all other threats, for example, the fire, disappear, as I made it disappear here. The other threats are still present, so we are in a situation in which we will have to do a design, for instance, for our fire safety engineering design, but take into account of the consequences that the pandemic might have on the crowd dynamics, and as well as the possible risk linked to the exposure of the occupants to the coronavirus. Which means that in this situation, evacuation models can be a great help, because those models, even if they are originally designed to deal with different type of problems, mostly problems linked to fire safety engineering or crowd management or space usage design and so on, they can be very helpful to address the problem of concurrent threats, like it can be COVID-19 and a fire threat. So the problem is that we know that there are all around the world some recommendations concerning physical distancing. So these can have both psychological and physical implications on the way people move. First of all, we know from the field of crowd dynamics that there are some rules of self-organization and some mechanisms that occur in crowds in relation to how they perceive others. Everything that has to do, for instance, with how much we walk close to others, how the mechanism of collision avoidance work, and so on. And those can potentially change due to the pandemic, because the situation is quite different here. So what happened is that as evacuation models, we can look at the field of proxemics and try to study and understand how the concept of personal space is now changing. So personal space can be interpreted now as a buffer zone, which means that others around us are potentially seen as intruders of our space. But the main limitation of this concept that is quite widely used in the field of proxemics is that the personal space looks mostly at the individuals. So you mostly look at the personal space intended as per one individual, rather than looking at the behavioral collective groups. That's why a good suggestion that I have on this is to look at the social identity theory, because this theory started looking at the psychological crowd. So basically started looking not at individuals per se, so how an individual behave or how a physical crowd behaves, so people that basically are just an aggregate that don't have any whatsoever bonds or social identity, versus psychological crowd which has a common identity, and this has all sort of implications on how they move. Like, for instance, a group that tend to stick together, certain type of groups that are more prone or to repulse each other, and so on. So a good suggestion for this is to have a look at the implication of social identity theory, and there are many recent papers that look at this in the field of crowd dynamics. From the point of view of physical implications, we all, I guess, have read about the change of space usage. So we know that, for instance, when we look at occupant loads in evacuation scenarios, the number of people allowed in a building is different. In a way, from an evacuation perspective, there are some good side effects, let's say, of COVID-19, in terms of the fact that generally less people are allowed. So in theory, the occupant loads are generally lower. From that perspective, we know that this has unfortunately very negative consequences on the businesses and the stakeholders that deal with crowds. But we know also that all the provisions that are given concerning physical distancing and space usage sometimes are very prone to interpretation. Here I just made an example linked, for instance, to how we implement this in the evacuation model. Evacuation models may use different assumptions for representing people, like, for instance, elliptical model or circle representation of people, and so on. And then depending on where we calculate the physical distance from the center, from the edges, so the interperson distance or the closest points between people, those physical distancing provision can change how much people we can basically fit in a given space. And this is just examples, because there are many things that are currently debated, which are also linked, as I said, to the way models represent people in their simulation. I'm mostly talking here and mostly have in mind microscopic agent-based models. So I'm mostly having in mind models that represent each individual as a single entity, single agent. And from the perspective of the fundamental relationships that we have in evacuation models, this can also be impacted. So if you think about the classic speed density or flow density relationship, those might change because there is more space between people. So all of a set of issues that were not really object of so much data collection now becomes all of a sudden important. For instance, I put here an image from a recent paper that I work with along with some colleagues from the UK here in Sweden, in which, for instance, we looked at the impact of crowd composition on egress movement, and we know that depending on the type of event or the type of crowd that we deal with, the groups that we have are very different. And this can have a very big impact also on the dynamics during crowd dynamics during COVID-19, because we assume that the group of people that come, let's say, from home or from the together to an event, they can be treated as a single entity. So we cannot just assume that people will all keep the physical distances, but the assessment of how these groups, the nature of these groups, and what are their dynamics, how collision avoidance work, for instance, between different type of groups, it's very important. And this has also implications indeed on all sort of assumptions that we do, for instance, of maximum density that we can assume, global density we can assume in a space. So not just looking at the local density, but the global density will depend indeed also on the size of those groups. And when it comes to the fundamental relationship between speed, flow, and density, basically we don't really have too much data, so we don't really know what is the threshold for unimpeded speed in terms of when people start decreasing their speed based on density in these conditions, because maybe people might want to avoid to get too close to other people, thus they start decreasing their speed before than the classical values or speed ranges that we see in current guidelines and handbooks, like for instance here I quote the SFP hydraulic model. So this is an important question that we need to address, and since we don't have data at the moment, we may want to make different conservative assumptions when we apply evacuation models for this scope. So we cannot just run an evacuation model with the default fundamental speed flow density relationship that we have in it, because those are based on data that were collected when there was no pandemic. And there is another aspect which is very important for evacuation, which we don't really know, and it is to which extent people will comply to physical distance recommendation during an emergency. That's something on which we really have a big question mark in our head at the moment as researchers and as practitioners. So it's important that we take this into account. So we try to probably evaluate different scenarios considering different assumptions about this. So how much people will weight the different threats. So here I show an example of the classic speed density and specific flow density curves that we are possibly all familiar with. And if you see, the blue curve is the classic hydraulic model that we have in the SFP handbook, but those may change, first of all, because the density, we might not be able to reach very high densities because people keep a larger distance between them. But we don't know to which extent, especially as I said, the nature and dynamics of the groups might impact what is the max density that we can have in a given space. And also we don't know, as I mentioned before, at which point the speed will start decreasing depending on density. People will start decreasing basically almost immediately, also with very low density, or if it will be something in line with what we saw in a pre-pandemic situation. So we don't really know how this the shapes of these curves look like, but we know that we cannot just use this default that we have here. So in reality, we will have something in between the curve that I put here, this light gray curve, and the blue curve that we have here. So another important aspect to take into account is that physical distancing might have also implications on route choice. We may think that people, when they approach a crowded area where there is a group, for instance, might decide to reroute to go somewhere else in order to not be exposed to be too close to other people because of being afraid of being exposed to those and being potentially exposed to coronavirus. So this is something that we don't really know. So it's another thing that we should carefully evaluate when we use evacuation models. So try to reason and think about what type of assumptions we can use for our choice, and maybe also think about if we need to modify the defaults that are in the model concerning the chosen routes by agents. And the same can be said for collision avoidance in general. So we know that people may want to possibly have a larger space in between them and others, at least between people of different groups moving in space. So while we have, I would say, a quite good understanding of how the collision avoidance mechanism work in a pre-COVID scenario, we don't really know too much about how it works now. So we really hope that more data will come out in the literature soon, so that we can have a better calibration of that at the macroscopic level of interactions between different type of flows. It can be unidirectional flows, it can be bidirectional flows, and so on. So big question mark here. We don't really know this. So the next part which I will talk about is the proximity analysis versus exposure assessment. So the idea here is that we know that the evacuation models, at least microscopic agent-based models, generally give us the location of people in space during the passage of time. So basically we get some sort of parametric equations of movement, which means that for each simulated evacuees, we have coordinates available at each time step. So generally this can be in 2D or in 3D, but basically we can keep track of each person in space. And this is very useful for us if we want to use this information for an analysis linked to the pandemic. Why? Because we can basically see how close people are to each other. And we know that at the moment there is an ongoing debate, and I'm far from being an expert of virology, but I read and try to catch up with the recent papers that come out in the scientific literature on the type of mechanism for virus transmissions. But we know that at the moment there is a lot of uncertainty. That's something that we know. So we know that we don't know. So this has implications on the type of approach that we can use to study the mechanism of virus transmissions, so, and the implications that they have on crowd movement. Because what we generally see nowadays is proximity analysis, which basically is an analysis that makes the assumption that risk increases with proximity. So the closer you get to other people, the higher is the risk. And this is something that was holding until we started having on the scientific literature a lot of debates on the fact that the coronavirus can be airborne, and this may have very different implications in building usage. Because, for instance, if we have an HVAC system or some sort of a ventilation system that brings air from a part to another of a building, then it's not just a matter of proximity to other people, but there are many more issues to deal with in a confined space. So we move here to a more general concept of exposure assessment. So risk does not depend necessarily only on distance criteria, but it can depend on different things, like, for instance, the configuration of the building and the ventilation in the building and so on. So I am more keen towards using exposure assessment rather than proximity analysis, because it is a more general way to deal with the problem, at least until we don't have the certainty on the mechanisms for virus transmission. And what kind of mechanisms we can have that we can consider in an evacuation model when we want to study exposure or proximity? Well, some are pretty easy to consider, for instance, physical contact. So when agents get very close to each other and they almost touch each other, or physical distance radius. This is something that a few evacuation models started looking at. So when you are within a given radius, then you can say that you are exposed. In reality, when we do an implementation of the physical contact, we possibly use a very small radius. That's what we generally do when we want to study this. And there is not too much, though, yet on, for instance, at least not seen this in crowd models, on looking at people dealing with objects, touching objects, which is a whole big question mark that we have nowadays. For instance, like how many times people touch a doorknob, and what is the associated risk to that. But potentially a crowd model could deal with that, so could produce outputs linked to that. And there are more complex ways that we could, in which we could use evacuation models. For instance, looking at face-to-face contact in physical distance radius. I've seen actually people starting doing, for instance, I know the group, some Finnish researchers started doing also looking at using CFD for studying transmission of the virus, and this could totally be coupled potentially with a crowd model in order to see, for instance, depending on the angle of interaction between people, what is the risk or the exposure. And if we look at the general concept of exposure assessment, we don't have to have people necessarily very close to each other. They might be simply in the same room or in the same building. So this is another assumption that we could use. So as I mentioned, I recommend to use exposure assessment because I think it is more general, and until the uncertainty is there on the mechanism for virus transmission, is a more general way to study this issue. And finally, I want to present this model that I work with along with my colleague Ruggero Lovrelio. It's a simple model. It's basically designed to retrofit any crowd evacuation model, and it works with any exposure assumption. So it's not linked to a specific assumption. So the idea here is that for every agent in the model, assuming a microscopic agent-based model, we know that it is potentially exposed to a given number of people. So we can get a set, including the number of people to which each individual is exposed to at a given time interval. And starting on from this set, since we have this information for each individual person, we can get a matrix. And this kind of matrix, it's pretty easy for an evacuation model to produce. So it's something that many microscopic evacuation models would be able to produce. And starting from that, we can do some assessment of exposure based on any of the assumptions that we have seen before, or other assumptions, which basically means we can take the information, we can obtain the information on the time to which an individual is exposed to a given number of people, k. So in this example, if I have 10 people, I can be exposed to max 9 individuals, and I can read the exposure time from a crowd evacuation model. And then if I look at the total time spent by people in a given space, we can obtain a set of distribution of exposure times, which corresponds to a given number of people. So in this same example, if I have 10 people in total, I have 9 maximum people that I'm exposed to, and then I have all these distributions, which means that I can have several information concerning the max number of agents that I'm exposed at the same time, so each agent, longer exposure time, and the whole distribution information, so average and variance. Which means that then if I do a summation over the data points available, I can get a cumulative exposure measure, which is very useful to compare different scenarios. So if I get the case of k equals 0, so if I'm not exposed to nobody, I can see that the higher is that value, the better it is. And all the others can give us an indication of a cumulative exposure to other people in the building. And then if I sum this up, I can have a global evaluation of the exposure. So basically, I can put some sort of a score on a given scenario in a given condition, a given evacuation condition, and see how people are exposed to each other. The potential issue is that we need to discount groups, because people that are already together from the beginning, they cannot be counted as people that are meeting inside the building. So this is an issue that has to be solved, and I've been discussing this with a few people in the evacuation modeling community, because it's still yet not solved. So the workflow to use this will be to define the crowd movement scenario, simulate the people movement, choose the occupant exposure assumption, and then getting the outputs, and then calculating the time of exposure, and then following the procedure that I showed before, reaching a global assessment of occupant exposure for a given scenario. And then I can do a risk assessment of building usage based on this matrix, which means that basically I can do then evaluation of design solutions or crowd management solutions. So for instance, I could have extra, let's say, separations between in an area to have to avoid bidirectional flows, but I have to also see what implication this may have if I use in a normal scenario or in an evacuation scenario. So overall, we are really much under the spotlight as a crowd dynamics community. We see the crowd movement behavior change due to the pandemic, but we don't have too much data, so we have to be careful in using conservative assumptions, and we can use proximity analysis and exposure assessment together with fire safety engineering to evaluate concurrent threats. So thanks, and if you want more information, here are some references of this work. Thank you.
It's a big rush.
It's the post-coffee effect.
That's right. So that was really interesting, and we're definitely interested in, we've been implementing some features in Pathfinder, but we're interested in also tracing exposure and contact and stuff like that. So it's really nice to have this model available for that. Since then, do you know of any other validation work or any way to?
I know, as I mentioned in the talk, a couple of people are trying to, a couple of research groups are trying to collect data. So myself, with some of the colleagues in New Zealand, we are trying to do some data collections. And I know the group at University of Navarra has been doing that, and also in the Netherlands, the group of University of Eindhoven. So, but we need this data because otherwise, okay, we know what are the mistakes that we possibly can do, but it's very hard to calibrate a model.
Yeah. Simo Hostika asked here about, now that airborne spread mode is being accepted in the scientific community, how would that affect the development of your model? That people still don't see aerosols. So
I think this is very important work that Simo and his colleagues did in Finland, because at the moment we still have the majority of the, let's say, modifications that have been done in evacuation models, mostly focusing on just proximity, but not really looking at the coupling between what we are actually briefing and where people are. So, I mean, and one of the biggest arguments that I had in my talk indeed was exactly this: we should transition towards exposure assessment, and the concept can be the same. We can still trace, I mean, as long as we have parametric equations of the coordinates of people from an evacuation model, and we generally have this information, we can still trace where they are, but we should somehow couple this with a bit more refined information. Exactly what, for instance, the example of what Simo has been doing and his colleagues in his work is exactly what I'm talking about. So moving away from just looking at the position of people, but trying to find ways to measure exposure of people.
Do you plan on integrating or testing your study in an advanced tool like FDS evac?
That's something I have to find a student to help me with. If I find a student to help me with, I'm more than happy to do something like this. But it's the point is, at least for who doesn't work with the commercial development like me, it's not more about putting something out immediately, but more trying to understand also what we should put out and raise the questions of what we should put out. Because as I say, I totally understand the rush and the pressure that companies like Thunderhead or many of the other evacuation model developers have to put something out to be usable for people. But we should not forget that there are several things that we first need to know before we can have, let's say, a comprehensive assessment of exposure of people. So my idea would be to first focus, if I have to put an effort now, I would put it more in trying to collect data rather than on how people move in these times of pandemic, rather than doing a model development, which people like Brian and his colleagues surely do much better than me.
Yeah, so, and we have been working with you in conversation about this as well. So and are trying to release helpful tooling for this kind of analysis. So so we have time about for one more question. What's your opinion about the future of evacuation modeling with COVID or future pandemics? Any new trends or research?
I think we're going towards the direction of even more coupling between crowd movement models and other models. For instance, actually since back in 2012, there were models trying to do coupling of epidemiological models and crowd movement models. For those who were at PED in 2012, the conference there was a keynote on this by a Swedish researchers, Anders Johansson. So this is not new, but I think if this COVID will not disappear soon with the vaccine, I think more and more people will start doing coupling of epidemiological models and crowd movement models, which is something for which people like me will have to talk to people that work in that domain, because of course it's our expertise in that domain is limited. But there are definitely possibilities to expand those two fields together.
Okay, great. So Enrico, we're transitioning over back to the stage now. I would recommend that you have a few more questions in here, starting with Judith and on down. So if you want to look through those and just make any answers here in text chat, please feel free to do so. But I'll end our little connection. So thank you very much, Enrico, for your talk.
Thanks
and for your participation. I'll see you later.
Thanks.